Deep inside an icy cave in Romania, scientists drilled out a 5,000-year-old layer of ice. Inside, a cold-loving bacterium was sleeping. It came back to life and shrugged off some of our strongest antibiotics. So if ice can preserve something like that, are we in danger as the planet warms and more old ice starts melting? Ice is like a library that files winters. Every new snowfall or drip of water that freezes adds a fresh layer. Scientists can slice through those layers to see what was blowing in the wind at the time. They find trapped dust, old pollen, or even stray microbes. The polar ice sheets are the biggest library of this kind on Earth, with books that stretch back over 800,000 years. But you do not have to travel to the Antarctic to find ancient ice. The planet has plenty of hidden underground freezers. One of the largest is the Scari Shoara ice cave in Romania. Tucked deep inside a limestone mountain, this cavern holds over 3.5 million cubic feet of solid ice. Getting down there is an adventure. Researchers descend a steep metal staircase about 160 feet into the cave. Standing on the frozen floor, they use hollow drills to carve out giant tubes of ice. Once, they pulled out a single core roughly 83 feet long, or about the height of an 8-story building. That ice dated back 13,000 years, long before human civilization. But the real surprise was the bacterium they found trapped inside. Bacteria are single tiny cells, basically microscopic bags of chemical reactions. They multiply by copying their DNA and splitting in half. This is a process called binary fission. If conditions are right, they can double their numbers in 20 minutes flat. Most bacteria that can infect us like it warm. Around 98.6 degrees Fahrenheit is their comfort zone, but the one from the Romanian cave belongs to a different kind. The name is foreboding: Psychrobacter. But don't worry, that only means it prefers cold temperatures. It does best in cold, fridge-like temperatures. Our body would be like a sauna for it, but that doesn't mean it's harmless to us. Ice preserves things by hitting the absolute pause button. Deprived of liquid water, the chemical reactions that normally break a cell down come to a complete halt. As long as the deep freeze keeps the cell intact, the germ can survive on standby for millennia. But give it some warmth and fresh nutrients in the lab and it wakes right back up. Scientists tested this strain against 28 antibiotics. It resisted 10 of them. The other 18 still worked, at least to some degree. But 10 failures out of 28 are enough to make scientists pay attention. Then they looked at its DNA. Inside, they found over 100 genes linked to antibiotic resistance, along with almost 600 genes we don't fully understand yet. There's also an important detail. Because this bacterium isn't common, scientists had to compare its behavior with that of similar species. So the resistance is real, but we cannot directly translate it into "this is what would happen in a hospital." In lab experiments, the tiny germ showed it could actively interfere with other microbes. Researchers identified 11 specific genes in its DNA that are linked to producing compounds that may suppress or inhibit bacteria, fungi, and possibly even viruses. In simple terms, it's like a small soldier wearing armor. That's antibiotic resistance, but it also carries a few spray cans in its backpack that can damage other microbes. That's not unusual in nature. Microbes constantly compete, and many survive by making molecules that harm their rivals. That's actually how many of our antibiotics were discovered in the first place. So this strain carries two important traits. It can tolerate some antibiotics, and it may produce its own antimicrobial compounds. That combination doesn't make it some unstoppable organism that can eliminate the human race. But it does mean it carries biological tools that had evolved long before humans started making medicine. Here's what makes bacteria like this potentially problematic. Not because it can sprint into your bloodstream and establish a new colony there. It's not built for human body heat. The real headache comes from how bacteria behave around each other. They actively trade genetic upgrades, not like football players trading jerseys. More like coaches exchanging playbooks and learning new tactics. Bacteria pass around tiny DNA rings called plasmids, which contain bonus survival instructions. Other times, germs simply pick up loose genetic code from their surroundings, like finding a dropped wallet. The bottom line? We don't want these antibiotic genes to somehow end up inside a modern bacterium that thrives in humans. Creating a supergerm takes a wildly unlucky chain of events. The ancient germ has to meet a modern one to hand over its DNA. Then the new host has to actually assimilate it. Most of the time, that process fails, but the planet getting warmer could change how often these accidental meetups happen. More mixing means more chances for those upgrades. And we don't have to guess how thaw can cause trouble, because we've already seen a real-world example. In 2016, a heat wave hit the Yamal Peninsula in Siberia, with reports of temperatures around 95 degrees Fahrenheit, which is basically beach weather for a place that's supposed to stay frozen. Soon after, an anthrax outbreak showed up in local reindeer, and there were human infections too. Anthrax is a disease caused by a bacterium called Bacillus anthracis. This bacterium has a survival trick. When conditions get tough, it can turn into a spore. It enters sleep mode and stays like that for decades. The heat helped thaw and disturbed ground that had kept those spores sealed off. And once grazing animals ran into them, the whole cycle started up again. But bacteria aren't the only microbes that cold can preserve. Viruses can make it through too. Scientists have actually pulled ancient giant viruses out of Siberian permafrost. They earned that name for a very literal reason. Normal viruses are so incredibly tiny that you need a highly advanced electron microscope just to see a blurry outline. Giant viruses are huge in comparison. They are physically larger than some bacteria. You could easily spot them using a basic high school microscope, and after 30,000 years inside a cube of ice, researchers successfully revived them. The viruses immediately invaded living cells and started making copies of themselves. To play it safe, the team used simple amoebas as test dummies instead of human cells. But if this can be done with a virus so old, could there be other viruses in permafrost? Maybe something that targets animals or even humans? The short answer is precisely that. Maybe. But hold on, there's no need for a bunker just yet. Viruses are biological specialists. They're extremely picky eaters. To infect a cell, a virus has to latch on to the outside like a key fitting into a lock. A virus designed to infect a woolly mammoth or a prehistoric amoeba probably has the wrong key for a human cell. Our biology is just different enough that the door stays locked. That said, we aren't totally in the clear. Scientists have found genetic traces of things we do know, like the 1918 Spanish flu and even smallpox, preserved in permafrost and frozen remains. But finding broken pieces of genetic code is very different from finding a fully functional virus that can boot up and start an infection. Most of the time, age and background radiation turn these things into harmless leftovers. The realistic threat is not an apocalyptic zombie plague. It's an ecosystem disruption. If massive amounts of ancient microbes flood the ocean, they might mess up the bottom of the food chain, knock out a specific plankton, and starving fish create a ripple effect that hits bigger animals. Melting ice is a slow-motion issue that plays out over centuries. Science and medicine are wide awake and watching. Humanity already has plenty of daily troubles, so prehistoric germs belong near the bottom of your worry list.